So this is a talk about something that I've been thinking about for the last couple of years. And it started with 2 years of nothing working, as in I trashed a couple of parsers and it just didn't work. And then last Christmas, while I was recovering from very slight surgery, I had an idea. And this is what this talk is about. So we're in the modeling workflow, and we're done. We found the right model we want, and we're happy with it. And then the next question is, what should we do now? And there's a lot of different things to do with it. Depends on what we want to do. It could be inference. It could be other types of abstractions. But what I'm really focused on right here is making predictions from this model we decided was the best model ever. To be able to do this, I have pulled out today this little model using the penguins data set we all know and love. I have a fairly simple recipe that deals with missing values. We create dummy variables. We remove some variables that doesn't seem like they're that useful, centering and scaling at the end. Then we're using the bonsai package to provide the party kit engine for a decision tree. We combine it all in a workflow and fit it. This is not a great model, but it's very useful to showcase everything I need for this talk. And we can use it to predict like we normally would. It follows the tidymodels prediction guarantee. It's always a tibble, and it always has the right number of rows, right name, and everything. To sidestep a little bit, I want to talk about one of my favorite packages that I didn't write myself. It's called Tidypredict. And what it does is that it allows us to take a fitted model and allows us to run predictions inside a database. And the way it does that is that it parses the model, extracts all the sufficient information, and then reconstructs our formula that can then be evaluated in SQL or something else because of the great work done, stuff like dtplier, dbplier, dbi, and all of that. That allows us to translate our code into code that needs to be run other places. And Tidypredict works with a lot of different types of models. We have linear models, we have forest models, other types of tree models, all different types of models. But it has a limitation. And the limitation is that we're only allowed one iteration. And this means that it ends up not being that useful for a lot of people, because if you have a recipe, it doesn't work. Because that's why it crashed for me, because if you try to recursively reconstruct a recipe and a model object together, you did for even a modest data set, you did like 50,000 character SQL strings, and it doesn't like that. For the same reason, we end up with a lot of redundant information that needs to be calculated over and over again. If you're working with a tree model, calculating when to split has to happen multiple times, and it's inefficient. And lastly, same reason, we have one iteration. We can't get easy classification probabilities because we can only get one vector out at the end. So we can't get a vector for each class. So we can get it technically for the 2 class, but then we're limited. And this is where my contribution to this whole problem is, where I added the orbital package. So stepping back one more time is we think about how any given model works. And a lot of times, especially when we're like just practitioners and we think we need to have predictions done, we think about these models as more of a black box of data coming in, predictions coming out. But sometimes we can peel back for some of these types of models, especially a tree-based model that I used. And we can see that it follows this tree-based structure where at first we see is the build length less or greater, like less or equal to some value. If that's true, then we find some other thing, and then at the end we have that's the prediction right there. Here is just the normal print that comes out, but we could rewrite it as a series of if-else statements that then is equivalent to prediction. And lastly, we could also turn it into a one-liner from using the taste-when function from dplyr, which is essentially what Tidypredict is doing. But we are not just working with the single model. We're also working with a workflow, which includes everything that happens before. Because you might have noticed that this tree used like a bill length cutoff point that was negative because it has been normalized earlier in this recipe. So we need to make sure that when we do the predictions, it needs the right data at the right time. So we can think of this recipe because it works sequentially. It comes in, it handles all the nominal predictors using step-up known, then all the numeric predictors with imputed median, and so on and so forth. But we can rethink this as a series of statements, much like in a mutate call. So at the beginning, we have some statements that looks to see if the values are NA, and then puts in unknown. Likewise, when we do the impute median, it's the same idea. We find out if the values are NA or not, and pulls them in. And we move on. And then step dummy, you know the drill by now. We can think of each recipe step as doing some calculations one after another in a sequential way, ending up with our predictions at the end. But if we notice in our statement at the end, not all the variables from earlier were used. The ones we have left is set male, bill length, and species chin strap. So now let's go in reverse. So now we go back up and look at when we send out all the variables, and we notice that only 3 out of the 8 variables at that point in time were used. So we can just gray out the rest. We continue doing this, going up now what we're centering, scaling, identifying the ones that needs to happen for later use, and so on and so forth. So now we identified all the calculations that need to happen to be able to provide prediction, and we just throw away everything that doesn't. So in essence, if we can do this math, we're able to provide the equivalent of a prediction. And that's in essence what the orbital package will do. So you load up orbital and run the orbital function on our fitted workflow, and it creates an object that has all the sufficient information to do predictions that are equivalent to the original predict method. Before I move on, I want to make it clear that this object by itself is quite small, and it doesn't require any of the previous packages to work. So if you save this file to a disk and load it up in a new session, you don't need tidymodels, you don't need parsnip, you don't need bonsai, you don't need nothing. You just need orbital. So that's already quite a bit decreased in dependencies right here. So now we have the object, we have 2 main things we can do, prediction and code generation. And I want to start with prediction. And we predict just like we did before. So with the orbital object, we can use the predict function on it, and we see that the predictions are identical to the predictions that happened through the tidymodels object, down to some rounding in like the 12th, 15th decimal place. But I want to take this a step further. So then we know that it works with a plain tibble. We can predict with it and get it back. But where it becomes interesting is if we set up a little bit of infrastructure, I here spin up an ephemeral SQLite server, and I put the penguins data in this server, I'm able to predict directly in the database. So these predictions are evaluated SQL that happens not inside R, in a database somewhere. So if you can give me a connection object and some data that matches the data that this model is fitted on, we can predict in it. And because we can do this, we can also do something like in a Spark database, directly in using everything that Spark has to offer, not inside R. Also works with things like arrow. The print isn't nice, but I promise that it returns the same thing. And it will also work with niceties like duckdb. So we have like on-desk prediction, but not inside the R session. The other thing and so basically, if you can give me some data in a way, we can predict on it. But there's another side to the story, which is a little bit how all of this works. And that is the notion of code generation. So I showed you how we can do predictions in a SQL database. But we can also just not use R anymore. We take our orbital object, and we bring back our SQL connection. Here we're using SQLite connection, and we use them together, and it exports out the SQL that when run in this database does the same thing as prediction. It's important to note that we need the right SQL, it needs to be the right connection for where you're using it, because all the different SQL databases have slightly different flavors and different names for things, but this should work on any known database that has support from the DBI packages. This is also the way that duckdb works, because the developers behind duckdb have enabled these translations. Let's try another fun thing. So we're going back into R, but we want to do predictions, but we actually don't even want to use orbital. We just want to spin up a Shiny app, and we want to have it lean and mean, so it runs fast and everything you need. So to do that, first we need a function that does the prediction. So we have a function here called orbital rfun. You give it the orbital object and a file name. And what it will do is it will write to a file a function definition that when applied to a data set produces predictions that are equivalent to the predictions we saw before. So with that in mind, and so this one needs dplyr because some of the steps needed dplyr to work, but it doesn't need audible, it just needs dplyr to work. So with that in mind, we can spin up a simple UI that matches the input that we're expecting. And the server side, we're taking all the input, putting it together in a data frame, putting it into this function that we sourced in, and now I'm just rendering it to text on our Shiny app. So now we have a slightly modified Shiny app, so it looks nice, but in essence, not using tidymodels, not using orbital, at least in the Shiny app, we have live predictions that does exactly what you expect. And we can take it one step further. So the same way I showed how we can generate an R function, you can use the same technique. So this isn't implemented, but I spent around 10 minutes with my very rudimentary JavaScript knowledge, and I translated the R function that was outputted earlier into a JavaScript function. And now we have tidymodels prediction using pure JavaScript in a website. So then we just we can slide things around, and it does the predictions the same way we would expect them to. In the browser, we're not using R, we're not using anything else. And this is just a simple JavaScript example to show what can really be done. You could technically also translate it to a Python function, so we can do Python predictions with from tidymodels. But you can also do Java, you can do C, whatever you have the domain knowledge to do, that is the right place for you to deploy this prediction model. All right, so I said a lot of nice things about the package, but there's some downsides. The main downside of why you don't want to use this package is that not all models are supported. And there's two reasons why not supported. One of them is that we haven't done it yet. And the other reason is that it is feasibly impossible to do. So that is models that, like distance-based models, like nearest neighbor models, you can't rewrite them as a series of expressions. It's going to be too long. But other types of tree or linear-based models could be implemented. So if you want them, file an issue and it can happen. Another major downside, which is the upside of using tidymodels, is that there's no input chatting. So it assumes that all the data coming into these functions are exactly as before. So if you have a new label in your factor, it doesn't know what to deal with it, and it might work, but it might crash. If something was expected to be a numeric but comes out as a datetime variable, it also probably will crash. But you're also gaining a slight speed in that way because we're not spending time actually chatting. And the last con, which will go away over time, is that this is very new. It was pushed to train about 15 days ago. And this is the first time I've told people outside my team about it. So, but it can do a lot of neat things. And this is where we come back to the pros, that we don't have to spin up a data container with all of tidymodels and all the extra dependencies we need. We can either use orbital or work straight in databases or skipping R entirely. And I see a lot of potential in this package. And this is where I'm going to lead off. This will send you to the documentation of the package, where I'm outlining a little bit more what it can and can't do.
Thank you, Emil. That was great. I look forward to using it.
Thank you.
So you touched on this a little bit at the end of your talk there, but does Orbital support all possible steps in recipes or only some steps supported?
I have implemented 46 steps. And there's some, I can make a list if people want of steps that will never be supported, partly because it needs to be code that can be translated into many flavors of SQL, Spark, duckdb. So any text preprocessing features won't work because you can't tokenize easily in SQL, and other things don't work. But if there's any step you need, let me know, and I will let you know if it's possible.
That's great. So how do you envision Orbital being used by data scientists? You touch on model deployment, maybe outside of R, directly in a database, but could it be useful for things like model comparisons or anything else?
So it depends on how you define model comparison, because this is only prediction. So it doesn't have any characteristics of the model. So it would only be a way of comparing how predictions work across models. So you need to save that. But this is a very lightweight object. So the memory footprint is easy.
So someone here asked the question that was on my mind. Where does the name Orbital come from?
So this was originally codenamed Weasel, because I needed a name that wasn't already used. And we tried a couple of different things. Orbital, it's like up in space, you're sending stuff out into production. It didn't feel bad.
Should we run Butcher on an orbital object?
Butcher doesn't do anything because it's already the most minimal object size possible.
Can Orbital optimize away the transformations done on input variables that are kept by folding them into the final model code?
So that is essentially what it's doing by not folding it in. Because if you fold it in, you get this recursive nature of it that ends up making the model object better, because you need to, when you're scaling things multiple places, it ends up taking a lot more long time. So it's the fastest you can make it using this convention. And sometimes it's going to be slow because we can't beat matrix multiplication, and this is not matrix multiplication. This is what it is.
So I see a question here about Python. I'll go ahead and ask it, but add my own at the end. The question is, how would this be integrated with Python? And my own question is, could someone maybe borrow some of this like idea and concept and implement it in their own in Python?
You could. Like, part of the reason why I made this package is I haven't seen anyone else do this for pre-processing. So people have tried taking a fitted model and extracting the prediction, but they never extended it to pre-processing as far as I know. But in theory, you should be able to follow this approach for scikit-learn models and pre-processing.
Well, thank you, Emil.
Thank you.